you have in your notes, you have the mean value theorem. This is on page 288 in your book, but why would you need that when I already gave it to you? Okay? So, the first, I will tell you, the FRQ that I graded this summer involved the mean value theorem. And so, one of the things that happened that we had to take points off for was not stating the conditions. I believe what they told us, I think they gave us a differentiable function, which implies continuity. Okay? And so that's going to be important. It doesn't go the other way around. Being continuous does not mean it's differentiable. Think about the absolute value function that we talked about yesterday. It's continuous, but it was not differentiable everywhere. If a function is differentiable, it is also continuous on that interval. And so stating those conditions is very important. You cannot use the mean value theorem as a justification or explanation without doing that. So this number 1 and 2 are very important that you state them on every problem that you do. And you got to make sure that it's actually true. Because if 1 and or 2 is not true, you cannot use the mean value theorem. Okay? What the mean value theorem states, and like I said yesterday, the Rolle's theorem is one specific case of the mean value theorem, and I'll explain that in a second, is that what it's saying is that the derivative at some value c, what does this thing on the right look like to you? Yeah, this fb minus f of a over b minus a looks like slope. So this is the derivative somewhere equals the slope. Now, so what this is saying is the slope, or sorry, this is the slope of the tangent line. That's the first derivative. Okay? And then this is just the regular slope. We're frozen again. Oh, we're doing the lesson. Don't you worry. All right, so this is the slope of the tangent line. Okay? That's what the derivative is. This is just regular slope. Now, what this is really saying is this is the instantaneous rate of change. At that instant where x equals c, that's the instantaneous rate of change. Okay, so as I was saying, this is the slope of the tangent line. Okay, pay attention, please. Hopefully this will work the rest of the way. This is the slope of the line that connects the endpoints. That's known as the secant line. That is the average rate of change, the regular slope from algebra. Okay, so what the mean value theorem states is that there's a point C, if these things are true, where the instantaneous rate of change, the slope of the tangent line, will equal the average rate of change, the slope of the secant line. This is just another rearrangement of that. That's what this is saying down here. There's going to be at least one tangent line at some x value equals c that will be parallel to the secant line because the slope of the tangent line is equal to the slope of the secant line. So this is again, Rolle's theorem is a version of this because if you think about it, the line that we connected from the endpoints in Rolle's theorem was a horizontal line. And we found a place where there was a horizontal tangent. So in reality, when we were connecting those two endpoints for Rolle's theorem, that was the secant line. And we found a tangent line where it had the same slope, 0, because the slope of a horizontal line, of course, is 0. Now, this is an example on this page here of a curve. Now, from this curve, I have two endpoints. It is continuous, it is differentiable. All right? Now, there's going to be a place on this line, and you're going to have to draw this in. There's going to be a x value c. Now, if I have a tangent line here, notice we have c now. Okay? There will be a spot, because what you really need to do here is connect the endpoints to get the secant line. Okay? So there's this value c where this tangent line and this secant line will have the same slope. This is a visual representation of what the mean value theorem is saying. It's continuous on the interval. It's differentiable on the interval. There will be at least one spot where the tangent line is parallel to the secant. And the instantaneous rate of change, which is the first derivative, is equal to the slope of the secant line, which is just connecting the endpoints. Okay? That's what this theorem allows us to do. Okay? Now, in your notes, we have two problems. Okay? So, as I stated at the beginning, when you have a problem that you want to use the mean value theorem for, you have to ensure that it is continuous on the closed interval and differentiable on the open interval. And so when we look at these problems, we have some look-fors. We look for variables and denominators. We look for variables under radicals. We look for variables with logarithms. And sometimes we look at variables with trig functions, because at some places those are undefined. With a problem like this that has none of those things, we can say that this is continuous everywhere. In particular, it's on this interval. So this, let me try again. So, and because it is does not have any gaps or sharp turns, because this is going to be a cubic function, it will also be differentiable on that interval. Once that happens, then what we have to show is that the first derivative and the slope of the secant line are equal to each other. Yes?
Why for one of them it's a closed interval and the other one?
Because we can't differentiate at endpoints, because there's a possibility of confusing whether or not there's slope of 0 or undefined there, so we just say there's no point there and we don't worry about differentiability at that end. Okay. Now, the first derivative of this is easy, 3x squared plus 1. Okay, and I already went ahead and plugged the c in. Because these conditions are true, there's gonna be a c. Okay, now I just need to find the slope of this line at between the endpoints of 0 and 2. So that's a matter of saying f of 2 minus f of 0 over 2 minus 0. Well, when I plug 2 in here, I get 8 plus 2 is 10 minus 1 is 9. When I plug 0 in, I get negative 1. So that just is 9 minus negative 1, which is 10, over 2, which is 5. So what the mean value theorem states is that somewhere along the way, this will equal this. And so we just have to solve that. And I would give you time to do that, but we've eaten up so much time with this that I'm going to go for it. Okay, so I need to subtract 1, divide by 3. So c squared equals 4/3. Then I have to square root both sides, and that requires me to take plus or minus. And the square root of 4, of course, is 2. And by now, hopefully, you know you can leave radicals in the denominator in calculus. Now, what we have to decide is I have two values, 2 over the square root of 3 and negative 2 over the square root of 3. Are they both on the interval? No. Which one isn't? Negative. The negative is definitely not on the interval. Now, the other thing that we can think about, so we can throw the negative 1 out, right? The next thing we need to do is check and make sure this number, 2 over the square root of 3, is inside of here, right? If this was a 1, then we'd be at the end point. So as this number gets bigger, the entire fraction actually gets smaller. When you divide by a smaller number, you're dividing it and it's turning into something that ends up being smaller than that, okay? And so the only way that this number would get bigger than 2 is if this number was smaller than 1. Think about it this way. If this was the square root of 4, right? This is obviously not the square root of 4. The square root of 4 is 2, and then this whole thing would be 1. So that's right in the middle, right? And so this one is going to be on either side of 1. Either way, it's going to be greater than 0 and less than 2. So we're good with that one. And if you wanted to punch in the calculator, you could do that too if you wanted to. All right. Part B, what number do I have to look out for? What's going to create a problem for us in B? Negative 2. That would make this undefined. Negative 2 is not on our interval. So we're good. It's continuous on the interval. It is differentiable on the interval. And so we're in good shape here. Okay. And so now we proceed the same way. I need to find the derivative of this, and then I need to find the average rate of change, or the regular slope for the secant line. So this is going to involve the quotient rule. So low d high minus high d low over low squared. And again, just in the interest of time, I'll show you that. Okay. Low, the derivative of the high is 1. Minus high times the derivative of this, which is 1. And I've already went ahead and plugged my c in. You do not need to expand this. Okay. So that's, and I can take it one step further and cancel the c's. And there's my derivative. So there's the instantaneous rate of change. That is the slope of the tangent line. Now I need to find the slope of the secant line, which is the slope of the line that connects these endpoints. Okay? So again, that's f of 4 minus f of 1 over 4 minus 1. When I plug 4 in, I get 4 over 6, which is 2/3. When I plug 1 in, I get 1 over 3, which is 1/3, and then I have 3 on the bottom. Okay, so this is what I get for my slope. Well, 2/3 minus 1/3 is 1/3. 1/3 divided by 3 is 1/9. So what we're saying here is that this has to equal this at C, and that's what we're trying to solve. Okay, and again, I would cross multiply. So this is 18 equals c plus 2 squared. Those of you who are wanting to expand this out, you can, but you don't have to. And I can tell you right now, because this is not a perfect square, it's really not going to, if you expand this out and bring it over, it's not going to be factorable. You're going to have to use quadratic formula anyway. Okay, so now again, I take the square root of both sides. What is the square root of 18 close to? Square root of 16, which is 4. So this is bigger than 4, less than 5, right? Because square root of 25. Subtract the 2 over, and now we've got to figure out if both of these work. Well, negative 2 minus 4 point something is still going to be negative, not going to be on the interval. Okay, so we know we can throw the negative out. Is this on the interval? Negative 2 plus 4 point something? What's it going to be? 2 point something. That's in there. So we're good. Okay. Now, the last two problems we've thrown the negative out. That's just because of the interval we were given. It's not going to be a standing rule where you always throw the negative out. All right, that just happened for this problem. Okay, for these two problems. Okay, questions so far? All right, moving on to the next two problems. Why does the mean value theorem not apply? That means it doesn't apply because there's a continuity issue or there's a differentiability issue. One of those is true. Okay? Is the tangent always continuous?
No.
Where wouldn't it be continuous? What's the tangent ratio? Think about your unit circle. What was it? Y over x. So if x is 0, we have a problem. So we're talking this interval 0 to pi. So we're in the first and second quadrant, 0 to pi. Where on that does x equal 0? What angle is x 0? Pi over 2 at 90 degrees on the vertical axis, positive axis, x is 0. The only other place is 3 pi over 2, which is not on the interval. And if I keep going, it's still not on the interval. So the only place, so it's not continuous at pi over 2. The tangent is not continuous at pi over 2. That's why this one doesn't work. How about this? Can any value go under here for x? Can I have negatives under here?
Yeah.
Sure you can. It's cube root. It's fine. Yeah, when this is an even index, then you have to worry about negatives under here. So I can put anything in here. So this is continuous. Okay, is it differentiable everywhere? What would be helpful to have? to find out if it's differentiable everywhere?
The graph.
The graph, yeah, what else? The graph of what? The derivative. Maybe we should just take the derivative. Okay? And that's one of the things that you should be thinking about. Well, this is x to the 1/3, so f prime of x is 1/3 x to the negative 2/3. Well, where does that negative 2/3, what does that really mean? That means I have a radical in the bottom. Any issues there? When would this not be differentiable?
0.
X equals 0. If x was 0, we'd have a problem. It's not differentiable at x equals 0. Okay, so that's what the problem is here. And 0 is in this interval. Now, if the interval didn't include 0, it'd be different. Okay, so here's what we're saying. It's not differentiable at x equals 0. And for you, probably the best way to figure that out is to actually take the derivative. Those are things you want to look for. Okay. All right, we have one more problem to tackle, and there's a picture of it, a graph. And this is going to involve a bigger concept now. So here it is. Okay. It says use the graph of f of x to estimate the values of c that satisfy the conclusion of the mean value theorem for the interval 1, 7. So this is not the entire graph. It is only a specific interval. So what I would do is frame it off to start with. And know that we're just focusing on that. Is it continuous on that interval? Yep. Is it differentiable on that interval?
Yes.
How do you know? No sharp turns. Okay. So then we could also say, and differentiable okay. So it meets the conditions. So what we should start with, what the mean value theorem states is that there's going to be at least one tangent line that is perpendicular to the secant line. So the secant line is formed by connecting the endpoints. So here's an endpoint, here's an endpoint. I just need to connect them, and then I have the secant line. That looks like this. Can you find points on this graph where the tangent line is parallel to the secant line? So what I want you to do is draw them in. There's more than one. Find where there are tangent lines parallel to this blue secant line. And then estimate the values of c, that's the x values, at those tangent lines. Go. All right, how many do you got? How many tangent lines do you see? How many c values that are going to be parallel? 3. Anybody with less or more? Nobody has more than 3? You have 4? 2? All right, let's look.
It says he has 4 T.
Oh, 4 also, got it. All right, here's one. It's probably a bad estimate of 4.5. I didn't even put it in the middle there. So let's fix that. 4.5-ish. Okay, there's one. Did you have that one?
Yeah.
How many had that one? Raise your hand. Good. All right, how about this one? Do you have that one? 2.7. How many had that one? Raise your hand. Good. How about this one? You got 3. Where's the 4th one?
Above,
Above, what do you mean?
like,
What's the C value?
like
good. I agree. 4. Anybody have other ones? Okay, so this is the general idea of the concept. Draw the secant line, find lines that are tangent lines that are parallel to it, and then you can just kind of eyeball it. Okay? Questions on that? Sorry about all those technical difficulties at the beginning. I wish I could say they were my fault. They were not. But it was still super annoying. Okay.